All right, everybody, let's get started. Our TAs for the class, they did a lot of work this weekend and got caught up on some grading. So all the homework 5 grades are done, and homework 6.1 is being graded. 6.2 is due today. How did the section homework assignment go? I had a feeling it was probably shorter than the last one, right? A lot less tedious. What if I told you there's only 3 more homework assignments left? I've got some stuff to show you here in a second. Okay, so I did a little bit of work over the past couple days just to get everything caught up. So the attendance grades are all posted and up to date on Blackboard. I still have a couple of emails from some students there. I had one student who asked a question about a previous homework I hadn't gotten to yet, but probably within the next couple of days I'll have everything sort of caught up and up to date. We really only have 2 topics left for the remainder of the semester. The first is what's going to take a good bit of our time, which is the concept of a shear and moment diagram. For you civil engineers in the room who decide to take structural analysis from the worst professor ever, just kidding, that's me. You are going to get very familiar with shear and moment diagrams. At least in here, there's going to be just a brief introduction for it because depending upon your field of study, what you need to do there changes a little bit. The other thing I wanted to do is go through this, okay? Because this is it. Let me fix a glaring typo. Hold on. Is that okay? Is that better? Because this is it. We're down to the wire. Okay. I just noticed I copy and pasted the slide here, so ignore these lecture numbers because this is supposed to be lecture 33 and whatnot. But I'll fix that here in a little bit. But today we're spending a 2-part. We're starting a 2-part discussion on shear and moment diagrams. Today is going to be discussing shear and moment diagrams for. The whole time. Hold on. All right, it's all right. Okay. I have to do it. I could have given you the professor look. Here's the professor look. I could have done that. I didn't do that. Actually, I just did. All right. So today we're beginning the first of a 2-part lecture on shear and moment diagrams. So today we're going to focus on concentrated loads, and then on Wednesday we're going to focus on distributed loads. Friday, I'm going to have to pre-record that lecture. Friday is our next green and white day. So what I'm going to do for that day is I'm going to pre-record that lecture. I'm going to cancel class, our in-person meeting. The way that this lecture works, we're not going to have a homework on this lecture until well after Thanksgiving break anyway. So it's a perfect lecture to sort of just pre-record, and as long as you watch it between now and when we come back from break, you'll be good. And because I pre-recorded, I can probably do it pretty quickly. So on Friday, we're not going to meet, okay? Unless we can make it up. I tell you what, do you want to make it up the Friday before break? Oh, are you sure? Oh, y'all aren't vocal this morning. I feel like we're going to have to make it up. There we go. Okay, goodness gracious. All right, I scrambled to put together this slide, so I noticed another typo, and that's our exam. This says exam 2. It's supposed to be exam 3. So here's what we're going to do. This week, we're going to meet Monday and Wednesday, and Friday, I'm going to pre-record the lecture on concepts involving friction. On Monday, we're going to review for our next exam, and on Wednesday, we celebrate, okay? And that exam's going to cover centroids, and it's going to cover structural analysis, so trusses and what we covered today and Wednesday. Because we're doing our exam on Wednesday and because we're caught up on our schedule, we do not need to meet Friday. Friday was a makeup day. Friday before Thanksgiving break, we cancel. Okay? Everybody okay with that? Then Monday, when we come back, we're going to continue where we picked up off on friction. This pre-recorded lecture just goes through some basic ideas involving friction. We actually roll up our sleeves when we get back. I only have 1 homework assignment on this, which is due that Wednesday. And on Wednesday, what we're going to do is we're just going to go through the class, sort of a whole start-to-finish review on what we've covered in Engineering 213, because Friday is going to be our Q&A for the final. Okay? Just like we've done exam review sessions before, only because the final is comprehensive, we'll do the review this day and we'll do Q&A on Friday. And that is Engineering 213, ladies and gentlemen. Does that sound good? So that means I need to get into the wonderful world of shear and moment diagrams. So let's get into it. Okay, so let's talk about shear and moment diagrams. And really what we're talking about here is a continuation of my example with the table. Okay, if I'm sitting here on this table, and my man here's got the samurai sword or lightsaber if he happens to be a sci-fi fan, and I'm sitting on the table and he cuts through the table falls down. Okay, or the table falls down and so do I. And the reason is that because inside that point, inside the structure, the table had developed internal forces that kept me in static equilibrium. And it is those internal forces that we as engineers want to know, because that's what we need to design for. Okay, so we looked at a common type of structure over the past couple of lectures, and that was a truss. Okay, now we're going to look at another common type of structure, which is a beam. Okay. Now, I don't expect you to be able to do a shear and moment diagram that is this involved by the time that we're done. If you take me for CE 312, we do this stuff all the time in there, okay? But I wanted to give you a graphical representation of what a shear and moment diagram is, okay? So, first off, they are incredibly useful tools for civil engineers. I put here civil engineers, but really it's for engineers in general. I will tell you this. I don't think there is a civil engineer, mechanical engineer, biomedical engineer in this room who won't encounter some sort of physical system in their careers that has something in it that's being bent, okay? Just period, okay? I don't care if it's a bridge, a car, implant, I don't care what it is, okay? Any physical system that you encounter as an engineer is probably going to have something in it that is being bent in some fashion. I mean, even this table, I'm sitting here on this table, the table is experiencing a flexural effect, okay? Now, what is a shear and moment diagram? It is essentially a graphical representation of, in the case of moments, the change in moments, or in this instance, the change in vertical forces along a beam. So it's basically a graphical representation of that. So to put it in perspective, okay, if I am sitting on the table and somebody cuts with a samurai sword or lightsaber right here, I can use statics to determine the internal shear and moment right here. But what if I cut here? Or what if I cut here? Or here? Or here? Or here? Or here? What if I cut anywhere along the beam? What is a shear and moment diagram? It is a graphical representation of those internal forces everywhere in the beam. That's basically what a shear and moment diagram is. And they're critical because there's no way to effectively design a flexural element without understanding these forces. Okay? So if you want to tie it to statics, this is sort of a representation of the change in vertical forces. This is a representation of the change in moments along the span. Okay? The reason that we use V for shear is because I don't know about you, but when I'm writing with handwriting, my number 5s and my S's tend to look the same. So I tend to use the letter V for shear because we're talking about a change in vertical effects. So that's why we use the letter V. Okay? So the idea is that, okay, let's say I was a mechanical engineer and I was looking at this flexural element and it had, distributed loads on it, point loads on it, what have you. What this shear diagram tells me is that I need to size this beam such that it can withstand a maximum shear of 46 kips, that it can withstand a maximum bending moment of 460 foot kips. That's what this shear and moment diagram is telling me. And without it, you really can't go into the land of design. Okay? Now, I am going to somewhat refer to a sign convention a little bit in here. I'll be honest with you, I'm probably not going to get too heavy into maintaining a consistent sign, or I'm not going to get too heavy into emphasizing this sign convention too much. This sign convention doesn't get too important until we start deriving equations for shear and moment. We're not going to do that in here, so you don't need to worry about that. But one of the things I will tell you is that if you remember in trusses, we did sort of adopt a sign convention, if you will, and one of the truss sign conventions that we adopted is that we said that all members that were experiencing tensile forces we would treat as positive, right? So when we were initially doing a method of joints or a method of section analysis, we would just assume everything was in tension. So if we got a negative answer, we would assume everything is in compression. Now for shears and moments, we're going to do something very similar. We're not actually going to use this sign convention very directly in here. Instead, we're going to kind of piggyback off of this in order to develop a graphical approach that's a whole lot easier. But the only thing I'll say about this is that with shears and moments, you really do have to, I guess for lack of a better term, there is a certain convention that you need to adopt when constructing them. Now, what you'll find is that the convention that we adopt, along with the graphical techniques that we use, is actually pretty straightforward and pretty easy. So we're kind of lucky there. Now, what I want to be able to do, and this is my goal, a shear and moment diagram is nothing more than a plot. It's nothing more than plotting shear and moments across the span. Okay, so that's my goal. Okay, remember, if I cut a section, that will determine the shear and moment at a given point. I want to determine the internal shears and moments everywhere. Okay, and so in order to explain how that's going to work, I want to look at a basic example. Okay, so I have here a beam. So let's take a look here at this beam. I have a beam. I've got my x-axis and I've got my y-axis, right? So we'll say here's my origin on this side of the beam. And I have some load on it. It doesn't really matter what the load is, so it's just some arbitrary load W of x. One thing I'll say is that I have the load pointed upward because it's a little easier to handle with my math. In other words, the load is pointing along the positive y-axis. But I'll show you how we're going to derive this here in a bit. Okay. Now I'm going to break out my secret weapon, which is a samurai sword again, or a lightsaber if I'm a sci-fi fan. But what I'm going to do is I'm going to cut out a little slice of this element. I'm going to cut out a little slice, that's like dxy. Y'all remember that in calculus, that term dx? It's a term that is infinitesimally small, right? So again, I've got that drawn this wide here, or like that wide here, but in reality, it's super, super thin, okay? And I propose that over an element that is, infinitesimally thin, I can assume that this variable load is just constant, okay? I can assume that's constant, and I really don't need to worry about handling the variability over an element wide that small, or an element width that's that small. Now, one thing that is worth mentioning is I do have my shears and moments plotted on here. Now what I have, if I look at my shears, I have an upward shear and a downward shear. Those are drawn according to the positive sign convention that I mentioned earlier. But probably what's most important to recognize is that I have some shear up here, and then over here I've got a shear plus some increment, plus some change. I argue that the shear and moment changes as I go along the span. The idea is to determine how much it changes. So I have shear on one side and shear plus some change. Moment on one side and then moment plus some change on the other side. By the way, don't worry, I'm not going to make you do this derivation on an exam or anything. So if you're like, ooh, what's going on here? Don't worry, I'm not going to make you do that. Okay? Now what we're going to do is we're going to take a look at this element. We're going to break out our equations of equilibrium and see if we can solve out what these changes are. Now let's start off looking at the sum of the forces in the y direction. This is pretty simple, okay? So what do I have? I've got V going up, so we'll take that as positive. I've got V plus dV going down, so we'll treat that as negative. And then what about this? Okay, I have W dx going up. That is the distributed load acting over the length, right? So if I had 2 kips per foot over a distance of 30 feet, that would be 60 kips, right? 2 times 30. So it's the magnitude of the load times the width. Okay? So if I carry out all of my algebra, I notice that a lot of terms cancel, like the V and the negative V, they cancel. And then I get a term that looks like this. That should be pretty familiar, right? That should look pretty simple, okay? Now, what about summing moments? What happens if I sum moments? Let's sum moments, and we'll say we'll sum moments on the right side of the element. So I have a moment going like this. That's negative. I have V times dx. That's also negative. What's going on here with this distributed load? I have the magnitude of the load times the moment arm. Now, how am I doing that? Well, if I take this distributed load, I can turn that into W dx, and then how far is that from the right side of the element? It's x over 2. So that's where we're getting, that component right there. And then finally, I need to account for that moment there. I'm not accounting for the shear, because if I'm summing moments there, that shear goes right through that. Now, when I evaluate all this out, I get this set of algebra right here, but then something's kind of peculiar. I'm sort of canceling that. Why am I canceling that? Okay? Well, here's why I'm canceling that. Remember, dx represents the width of this element. How wide is dx? Really tiny, right? What happens if you take a really tiny number and you square it? You get a really tiny number, okay? So I know that if anybody in here is a math major or whatnot, they probably hate the fact that I'm neglecting some of these higher order terms. There are topics in structural analysis where we do need to consider higher order effects. A good one is when we look at earthquake engineering and whatnot, or vibrations in machines and whatnot, but we're not going to really worry about that in this course. But what we can do is say, for those higher order terms, we can neglect that, go through our algebra, and then we get these very nice plug and chug relationships, okay? And so specifically what the money is after all that derivation is we can develop a pretty nice relationship between applied loads and then resulting shear and resulting moment. And what we find is that if we're looking between loads and shears, if I have the loads and I integrate those loads, I get the shear diagram, okay? And if I have the shears and I integrate those, I get the moment diagram. And I'm sure some of you are thinking, oh no, more calculus. It's 8 o'clock in the morning. My coffee hasn't kicked in. Are we really going to have to do a lot of calculus? Not really, okay? I think that this relationship is important to understand, but we are not going to be breaking out a lot of the straight up derivative and integral functions when we plot shear and moment diagrams. The relationships between these functions, however, are very important, and that'll become clear as we start to get into some of our examples today and Wednesday. So to give you an example of what I'm talking about, let's go to some basic math. What is the integral of 2x? Somebody. What is the integral of 2x with respect to x? Say it again. Who said that? So just x squared, right? Now, if there's a math major in here, they're very upset because you forgot something. Plus c. Got to remember that plus c. Plus c matters. I'm just messing with you. No, you're 100% right. You're 100% right. But let me ask the question a little more generally, okay? So what I gave you was the equation y equals 2x. And I asked you to integrate that, and you gave me x squared, which is correct. Now let me ask it another way. Y equals 2x. If I were to graph y equals 2x, what would it look like? It's a line, right? Let me ask it another way. If I give you a linear function, any linear function, y equals mx plus b, doesn't matter what it is, and I ask you to integrate a line, what does that yield? Say it again? Well, yeah, it yields the area of the curve. I'm talking about the function. If I integrate a line, what do I get? You get a parabola. You get a quadratic function. Does that make sense? Like if I integrate any line, if I integrate 3x plus 6 or negative 9x plus 15, whatever the line looks like, if I carry that through and integrate that, I get a line, or I get a parabola, okay? This is a very important relationship that we will see when we construct shear and moment diagrams. For example, if I have a region on the shear diagram that is linear, the corresponding region on the moment diagram is quadratic. If I have a region on a shear diagram which is constant, the corresponding region on the moment diagram is linear. It goes up one because that's what we're doing. We take our load, integrate it, get the shear, take our shear, integrate it, and get the moment. I'm not saying that the integrals, actually evaluating the integration by parts and all the stuff you learn in Calc 1 and Calc 2 matters. I'm saying that at least for our graphical approaches, this stuff is going to matter. For example, if I integrate this, I get this. The slope of this line is equal to this constant value. Stuff that you sort of pick up when you start looking at these integral patterns. Don't worry, we've got some examples that'll really sort of illustrate this pretty well. Here's going to be the conclusions that matter the most for the examples that we look at. If we look at the relationship between load and shear, what we'll find is that at any point, whatever the slope is on the shear diagram, that equals the load that's on the beam. And between any 2 points, the change in shear is equal to however much load that you place on the beam between those 2 points. And we can make similar relationships or similar observations between shear and moment. Okay, and if you look at our final conclusion, the change in moment is equal to the area of the shear diagram between these 2 points. When I see this term change in area, you think, come on, Dr. Mike, if you see change in area, that means there's area, that means you're going to have to do integration. Well, yeah, but this is a very graphical approach. I don't think I need an integral to tell me what the area of a rectangle is or the area of a triangle is, but I can still use those same patterns to develop an approach. Now, let me show you how this is going to work. We're going to start with concentrated force effects. Okay, so these are beams that just see concentrated loads. Okay, now what you will find when you look at concentrated loads, again, we've got that similar approach. Okay, so let's say between 2 points on the beam, if all I've got are point loads, then there's going to be regions on the beam that have zero force on it. Now, if I integrate 0, what do I get? The integral of 0 is 0 plus c, right? So if I integrate 0, I get a constant, and if I integrate a constant, I get a line. So if I look at my beam, let's say I have a beam that is experiencing just concentrated force effects, what I will find is the shear diagram kind of looks like this. It has sort of a stair-step feature to it, okay? And if I look at my moment diagram, I see a bunch of linear functions along the moment diagram. Whatever the value of the shear diagram is here is equal to the slope here. The value of the shear is equal to the slope. That's why the moment diagram goes high slope, low slope, because we have high shear, low shear, okay? Whatever the jump on the shear diagram is right here, it equals how much load's on the beam. Now, these are a lot of really pretty pictures. I think the best way of going through this is to actually evaluate it, okay? I want to look at this beam. That was loud. Now, first off, one thing I'm going to point out is, haven't we looked at this beam before? Now, I can tell you we did look at this beam, but I remember this beam very well because this was the beam where we had issues with the monitor and I broke out old school and did it on the chalkboard. So I am going to go through and calculate the support reactions on this beam again, okay? But I'm going to go through that part kind of quickly, but hopefully that part should be pretty simple, okay? So let's see. We have a pin support here at A. We have an A, Y, and an AX. And we have a BY. Now, first off, if I sum forces in the x direction, what does that tell me? Exactly right. AX is 0. It's 100% right. Okay? And I'll go ahead and tell you, for shear and moment diagram problems, at least ones that we deal with in here, most of these problems, that's going to be the case. Because with shear and moment, at least from an educational perspective, I'm more interested in the change of vertical forces than I am the change in horizontal forces. The change in horizontal forces doesn't affect the shear diagrams anyways. Now for the vertical reactions, I'm going to sum moments at A. So what do we got? So we just go through, we ignore the reactions at A. So 20 times 6, 30 times what? What's the moment arm for this 30 kip load? 15. For the 18, 22, and then BY times 30. The BY times 30 is going to be positive. So minus 30 times 15, I think that's 450. Minus 18 times 22. Okay. Combine all these. And again, this should be like we already did this problem, so I'm going through this part kind of quickly. So I'll just abbreviate that. And then BY is that. And so if I want to sum forces into Y, just sum those up, substitute. Then that is 68. I'm going to give everybody a sec to sort of catch up on that. But again, this should not be really all that challenging because we've done this before, okay? I see a couple people writing this down. But we did this problem together in class a few lectures ago. So everything up until now is just regurgitating what we did a while back. Go through this. Are there any questions about this? Okay. Does anybody need a little more time? Okay. All right. So let me scroll down here a little bit, and I'm going to cheat a little bit because I have my beam redrawn. Okay. And I'm going to indicate my reactions right here. So this one's 32.2 kips, and this one is 35.8 kips. Okay. Now, in order to handle this, okay, what I'm going to do is I'm going to draw my shear diagram here, and then my moment diagram a little bit below. You probably saw in that initial slide kind of like generally what they look like. So in order to do this, I'm going to draw a series of guidelines that sort of go down like this just to sort of keep everything lined up. Okay, so as you're drawing this on your calculations, just be prepared. There's going to be a lot down here and a lot down here. So let's see. So we'll sort of do that. Let's do that. Let's do that. Okay, that's enough for right now. All right. Now, the first thing I'm going to do is I'm going to strike a solid line. Okay. Now, sometimes when I'm drawing the shear diagrams, I kind of like to put little like tick marks on here. To be honest, probably not necessary for what we're doing in this class, but I kind of like it to be well known what the zero line is. Because when you draw a shear diagram, it's like you're going up, you're going down, you're going up, going down, going up, going down. I just want to make sure that it's clear where zero is. Okay? Now, what we're plotting here is the shear diagram. So I'm going to write, okay, that this is the shear diagram out here. And typically what I like to do is say that this is in kips, okay? And then as I'm drawing the shear diagram, I don't want to worry about writing units over and over and over again. So I'll just state it at the very beginning and then sort of go on from there. Okay. So far, so good? Now, okay, so here's how a shear diagram works. A shear diagram is a plot of the change in vertical forces along the span. So, this is a static problem, which means that the sum of the forces in the vertical direction is 0. Okay? Now, how that relates to this is that this problem better start at 0 and it better end at 0. Okay? Let's see if it does. Okay? Now, how do you draw a shear diagram? The simplest answer, you do what the beam tells you to do. So, I'm looking at this beam, okay? I'm here at A. I'm here at the left. And I look at the beam, and the first thing that I see is the beam saying, Greg, go up 35.8. So, I'm here at 0. I go up 35.8. That's what I see. Now, next question I'm going to ask you is not a trick question, okay? How much load do you see on the beam between here and here? It's not a trick question. What's between here and here on the beam? Nothing. There's nothing there. So, I go up 35.8, and then nothing changes. Nothing changes. Nothing changes. Nothing changes. Whoa, Greg, go down 20. Okay, so I'm at 35.8. The beam's saying, Greg, go down 20. If I'm at 35.8 and I go down 20, what's that put me at? 15.8. So that's about, I don't know, right there. This is 15.8. Okay. Now, how much load is between here and here? Nothing. So, I go over, go over, go over, go over. Whoa! I'm at 15.8. The beam is telling me to drop down 30. If I'm at 15.8 and I go down 30, what's that put me at? Say it again? No, negative 14.2. Then I go over, over. Whoa! I'm at negative 14.2. The beam is telling me to drop down some. How much is it telling me to drop? 18. So if I'm at negative 14.2 and I go down 18, what's that put me at? Negative 32.2. And whoa, I'm at negative 32.2. I see a reaction that tells me to do what? Which is going to bring me right up to 0. That, ladies and gentlemen, is a shear diagram. There's a lot that this beam tells you that you probably aren't going to appreciate just yet. You will definitely start to understand next semester when you take 216. So, like, as an example, if this was a concrete beam, what it would tell me is that I need to place a lot of shear reinforcement near the ends, but not so much near the middle, okay? Because the middle doesn't have as much shear force on the beam as the ends do, okay? Which makes sense because that's where there's where the reactions are, okay? Simply supported beams tend to need more shear resistance at the ends and more moment resistance in the middle, as you'll see here in a second, okay? Well, let me stop for a second, see if this part makes any sense. Everybody good on this? Okay, now, I remember a little conclusion that I had made a little bit ago that said that to determine the moment diagram, I need to integrate the shear diagram. But somebody made a point about what is integration? Determining the what? Area under the curve? Do I need to break out integrals to tell me what the area of that is? Really? No, I don't. Okay, let's keep this simple. All right? I don't know about you, these are rectangles. Let's start off with this rectangle right here. What is the area of that rectangle? How tall is it? 35.8. How wide is it? 6. What is the area of this rectangle? 214.8. Do I have a second? So what I'm going to do is I'm going to write plus 214.8 under that rectangle. Let's keep going. What about this one? 15.8 times 9. So you get 142.2. So we'll say plus 142.2. All right. How about this one? This third one. 14.2 times 7. Negative 99.4. Second. Last one. And she's good for the day. Somebody else. She's been putting in some work. Now, I didn't hear that. You're going to have to help me out.
Negative 257.6.
There we go. Do I have a second? Now, watch this. Because this is crazy. Let's sum those areas up. What do you get when you sum those areas up? 0. Interesting. It's almost like integrating the shear diagram will tell us the moments, and it's almost like the sum of the moments are 0. It's almost like this beam is in static equilibrium. Okay? One of the things about shear diagrams and moment diagrams is that they inadvertently can serve as a check for your reactions. Okay? Let me give you an example. Okay? I have 20, 30, and 18 going down, right? How much is that? 68 going down? Is that right? Okay, so 68 down, if I had said that's 34 and that's 34, if I had done that, I would have gotten a shear diagram that started at 0 and ended at 0. That would have worked. Then I would have started looking at the areas, and I would have found that the sum of the areas is not 0. Okay? Those two reactions are the only reactions that will cause both the shear diagram and the moment diagram to start at 0 and end at 0. They are the only two reactions that will keep this beam in static equilibrium. So they inadvertently serve as a check for that. Okay? So let's illustrate that. Okay. All right, so we're going to strike a line just like we did last time. I'll sort of strike a line there. Now we're going to draw a moment diagram. And as we saw from the areas, we are going to start at 0 and we're going to end at 0. Okay? Now, for this problem, I'm going to just show you how to draw this moment diagram, then we're going to explain some things about it. Okay? Now, from here to here, we look at our areas. And our areas jump up 214.8. So maybe about right there. And so what we have is a straight line segment going like that. And I'm going to explain why it's a straight line here in a second. Got some people peeking in. Okay, we got time. 214.8. Now, we're going to go from here to here. If I'm at 214.8 and I go up this much, where does that put me? Somebody help me out. 357. So that's going to be maybe something like that. Now I'm at 357. I dropped down 99.4. What does that put me at? 257.6, right? And then drop down to 0. Now, I got a lot to say about this moment diagram, so we're not going to jump away from this just yet. But that's our moment diagram. Now, let's see if we can understand some things about this. Okay. Help me out. If I wanted to graph that function, what's the function? This one right here. If I wanted to graph that, what is that? How do you graph a horizontal line? Y equals the number, right? So if I wanted to graph the line y equals 6, it's just horizontal line like that. Now, if I integrate y equals 6, what do I get? Integrate. If I integrate, not differentiate, if I integrate. If you integrate 6, what is the integral of 6? 6x plus c, right? The integral of any constant is that constant times x plus c. The integral of a constant is a line. So that's why for every one of these constant shear regions, linear moment regions. That's why they are lines. And they are not going to be lines on Wednesday. Okay? Now let's see if you're paying attention. What's the slope of that line? You don't need to do any math to figure out the slope of that line. 15.8. The slope of this line is equal to the shear diagram. Remind me, I seem to remember in the land of graphing that lines that look like this have positive slope, and lines that look like this have negative slope. It's kind of funny how up, positive slope, positive shear. How about this? Negative slope, negative shear, negative shear. We can also determine the magnitude of the slope by looking at the line. See, this has got a lot of positive slope. This one, not so much, right? This one has a slope of 15.8. This one is a slope of 35.8. It's kind of funny how it's got a steeper slope than this one, right? Crazy stuff, isn't it? Same thing here with this negative and negative. All right, we'll stop for a second. I want to see if anybody has any questions on this. So let me tell you, let me just give you a little bit of an understanding of how this would work in the land of engineering. So for example, if you were designing let's say a reinforced concrete beam, okay? What this moment diagram tells me is that, first off, the fact that it's in positive bending tells me I need rebar in the bottom, right? If positive bending, the top's in compression and the bottom's in tension, and concrete does not like tension, so I put rebar in the bottom. It also tells me to put more rebar near the middle than I need in the ends on the bottom. Okay? So that's kind of the analogy to how this works in the real world. Same thing might be of an element. Let's say in a machine system, I might need to stiffen the element that's near the middle for flexural stresses. So yeah. Does anybody have any questions on this? I'm going to take this problem and make it more complicated on Wednesday because I'm going to add distributed loads. And what hold on, stop. Yes, sir.
Never mind.
It's fine. Next time, we're going to look at distributed loads. Distributed loads are going to create linear shear diagrams and quadratic moment diagrams. But we're going to get to that later. I'm going to pull up the QR code again, but that's all I got, everybody. I will see you all on Wednesday.